winds. There's the little scale winds, the medium scale winds, and then there are the planetary or macro scale winds. So we talked about how there are 3 cells actually. There's 3 cells in each hemisphere. By my count, 3 times 2 is 6, but they always call it the 3-cell model. The polar cell is the top of the 3 cells, and we talked about this last time we were here on Wednesday. At the poles, so what you're looking at is the equator is here, so this is 0 latitude, and this is the southern hemisphere, and this actually is the northern hemisphere. So we're kind of looking at a cross section. The cells actually top out at the top of the troposphere called the tropopause. Okay, so we have cold air coming down from the poles, and it's deflected to the right in the northern hemisphere, so that makes it easterly. Makes it a surface easterly. We are part of the ferrule cell, I said. Okay, so this is a surface easterly. This is us. We are in the ferrule cell. We're between 60 and 30 degrees latitude. Okay. Then actually kind of butting up there about 60, we have some opportunity for some kind of crazy weather, because you have the warm air coming from the ferrule cell and the cold air coming from the polar cell. So they call that the polar front. So there now you can see all 3 cells in the northern hemisphere. We start out with the Hadley. Going north we have the ferrule, and then going farther north we have the polar. And again, there's like this says, a mirror image in the southern hemisphere. Okay, so jet streams. Jet streams, actually, again, in both hemispheres, there are 2 jet streams. So 2 times 2, I'm looking at 4. So there's a total of 4 jet streams. And you can see those 4 jet streams here. The dark line is the equator. Jet streams, these are kind of showing a little bit of waviness. The waviness is called meandering, like you kind of meander here, you meander there. It's called meandering. So sometimes they're kind of straight, sometimes they meander a little bit. Again, these are these are large scale winds. They're fast moving. Okay. And I always think of that movie Finding Nemo, where I don't know what relationship he was to Nemo, but they take, was it the turtle maybe? He takes the fast moving ribbon of water, not air, but it kind of reminds me of the jet stream. Okay. Jet streams, they are located between of the 3 cells we were talking about, the polar, the ferrule, and the Hadley cell. The 2 jet streams are located kind of between cells. So we have a polar jet stream located between the polar cell and the ferrule cell, and a subtropical jet stream located between the ferrule and the Hadley cell. So you're kind of looking, again, cross-sectional. I like this figure because it kind of shows you these kind of storm clouds here, kind of like cumulonimbus clouds here, maybe cumulonimbus clouds here. Of course, they're precipitating and make some type of nimbo or nimbus cloud. But what's creating that situation is this rising air we have between the polar and the ferrule, and the rising air, of course, we have between the 2 Hadley cells, right where the intertropical convergence zone is. So the polar jet then is between the ferrule and the polar cell. So one of the questions you guys answered in lab yesterday, and you did great in lab, by the way, is like how could you take a cold air mass maybe that forms here and get it to move down? And actually this is one of the answers, is this jet stream can kind of, if this jet stream, this is the polar jet, was farther south, it could actually relocate that air mass. Okay, so I guarantee it'll probably be in the form of a figure, maybe like this. You're gonna have to label some things with regard to where things are. You can already see the cells are drawn over there on the right. Okay, so I'll put an H here for Hadley, or HAD for Hadley, an FE or an F for ferrule, and a P for polar. So Again, Hadley, Ferrel, polar. I just get a kick out because 3, nope, I'm looking at 6. So we have some consequences of those circulation cells. One of them, I talked the other day, and I tried to find a good video on the whole horse latitude thing. Remember I said it's a sad story that actually in the horse latitudes, sailors sometimes had to lighten their loads so they would throw over horses. So you can see where the horse latitudes are located. They're located between the Ferrel and the Hadley cell. And then the reason, by the way, that we have little to no wind between the Ferrel and the Hadley cell has to do with this descending or air that's coming down from upper elevations. Okay, we talked about deserts. We get deserts there. It creates this kind of high pressure, subtropical high. We have a subpolar low here between the Ferrel and the polar cells. Why would we have a low? Well, because air is going up, creating a low pressure. We've talked about the intertropical convergence zone. It's near the equator, but it wanders. Sometimes it wanders relatively far from the equator, but that's the hot spot. That's where the word convergence in an intertropical convergence zone comes from those trade winds converging from the southern and the northern hemispheres. So they're actually similar to the horse latitudes. We have for a different reason, we have not much wind. That's called the doldrums. I liken it to an egg. I didn't bring my globe in here today, but if I would go to the North Pole and crack an egg, it would kind of go down like that. And so cold air is so dense that creates a polar high at the North and South Pole. And remember, wind is always going from high to low pressure. That's all. Wind is air relocating from high to low pressure. All right. So one of the things we talked about in the previous part, I think, was we said around a high pressure, and sometimes I get this wrong. Ugh. So this is a central high pressure. And we'll go ahead and draw the isobars. They're usually pretty blobby, actually. And here's a central low. You guys in your lab yesterday told me that this is going to be cloudy, right? Maybe precipitation. And you said that this is going to be clear and dry. That's one characteristic about the surface low and surface high pressure. We call this a cyclone, and we call this an anticyclone. And actually what makes this an anticyclone is it goes opposite the way the Earth spins. And we said the Earth spins counterclockwise, so actually motion of air is going to go clockwise. Okay, so motion of air is going to go clockwise. My other pen. Goodness, two dots. So around cyclonic motion then is counterclockwise, the same way that the Earth appears to rotate if you're looking down at the North Pole. This is in the northern hemisphere. It's opposite in the southern hemisphere. If you've ever heard the old adage, if you get kidnapped and they take you somewhere on an airplane and you don't know if you're in the northern or southern hemisphere, the old adage, you can look you can flush the toilet and see which way the water spins to know which hemisphere you're in. I don't know, that's pretty geeky. And it would work if your toilet had about as much water as Lake Michigan. So you need a lot of water to get a sense for the rotation of the Earth affecting it. So that's what's causing this. So anyway, I wrote that because of this. Okay. So we talked about there's a relative high pressure with that descending air about 30 degrees, and there's a relative low pressure with that ascending air about 60. So here in a minute, we're going to see those, what we call semi-permanent highs okay, in the winds. The red arrows are the winds, okay, and the black lines there are kind of like the isobars, like we did in lab yesterday. So if this is a high, we should look for this sort of motion. So high, that sort of motion. Low, okay, we should look for this sort of motion. Now that's the northern hemisphere, and it's opposite in the southern hemisphere. So let's see if it is. So a high should go counterclockwise in the southern hemisphere, which it is. I don't have any low to show you. The wandering intertropical convergence zone, if this is in January, we're pretty darn cold. So in January, you would expect it to be kind of south of the equator. That purple line, ITCZ. And 6 months later, in July, you can see the purple line has moved up, and you can kind of see some differences in the semi-permanent highs and lows. Here in a minute, and it's not that earth-shattering, we're going to talk about the ocean currents. These are winds. Okay, we're going to talk about ocean currents, and as it turns out, actually, the ocean currents are directly created by the wind that's going over it. Okay, makes sense? So the word is opposite. It's opposite in the southern hemisphere. And the reason we have this spin is the Coriolis force, CF. Okay. Actually, I'm going to pick on the most obvious monsoon, but we actually have monsoon seasons in Arizona and kind of out our west. But all monsoons, I'm used to seeing on the news like, oh, the monsoon season's here, and then you see all the rain, blah, 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 blah. But actually, monsoon seasons come in pairs, wet and dry. And a place has a pair of monsoon seasons if it's kind of near the intertropical convergence zone, or because of the wandering intertropical convergence zone, it gets differences in its precipitation. So India is a great place for a pair of monsoon seasons. So let's see what that looks like. So first, find the intertropical convergence zone. Okay, you can see, and we called it orographic lifting, where mountains, in this case the Himalayas, actually give a place for air to be lifted up as it's shoved up against it, and when it comes over on the other side, it's dry. Okay, this is dry. So the winter monsoon season is dry for India. Now, let's see what happens 6 months later. Well, 6 months later, you see the intertropical convergence zone is moving up north. Okay, so now its prevailing winds have changed, and actually you see, again, orographic lifting from the mountains, but now what it's lifting is not dry air. Now what it's lifting is this moist air from the Indian Ocean, I'm guessing. Okay, and so with lifting air, you can get precipitation, so that's why it's so darn wet there. So India experienced monsoon seasons, which is aggravated by the presence of the Himalayan mountains. We said there are 4 ways of getting a chunk of air to rise. If it rises, it cools. If you got a high humidity, we can have condensation occur. Enough condensation, you can have precipitation. All right. So I already mentioned that what creates these ocean currents, we'll call them large basin ocean gyres, I like that word too, is actually just wind going over the large bodies of water. So here are 5 major ocean gyres, and one of the things that ocean gyres do is they, well, of course they give us transportation, but they also allow transportation of cold water down towards the poles. From the poles we can transport warm water up. So it's kind of an equalizing sort of thing. So if I could go ahead and, let's see, this looks like it's, we got about 30 here, 30 degrees or so. I could put a semi-permanent high pressure there, okay? The letter H there. That's that semi-permanent high between the Hadley and the Ferrell cell. And so around a high, we know that wind moves clockwise in the northern hemisphere. So you can see that movement clockwise. We go ahead and pick on that one, that gyre. You can see that we have warm water coming up and cold water going down. So it's a cooling effect. It helps move thermal energy around. Okay. This term didn't make it to your test this semester, but I think it's kind of a cool one. It's called upwelling. And what upwelling is actually, it's the vertical motion of water. Now, I'm talking going down into the water, vertical motion of water, okay? And here's why that happens. We said that actually both Hadley cells have an easterly trade wind. You can see that black arrow showing your easterly trade wind. When this easterly trade wind is doing its thing, what it does is, this is South America over here. What it does is kind of draws water up from lower portions of the ocean up. So I don't know if you can see this, but the word is cool there, and it's actually going to be nutrient-rich water. Okay. And the good thing about the nutrient-rich water is that cute little fish are enjoying it, and if cute little fish are enjoying it, getting fed their belly full, then if you're a fisherman, you can go do your thing there. Now, I'm going to talk about something that's, if this is normal, okay, what's not normal? Well, there's two options for not normal, and they're El Nino, if you're like, and I'm not, Spanish was like way long ago, but you know, if it's a male sort of thing, you end in O and you begin with L. So El Nino, if it's female, you end in A and begin with La. That's about the extent of my Spanish. Okay, so we have El Nino and La Nina, that is kind of the opposite of these normal conditions. So normally we have a decent trade wind. Okay, so El Nino conditions also have to do with the trade winds. But what happens here is the trade winds actually peter out or sometimes even reverse. And you can kind of see what happens there. The red is indicating kind of warmness here over South America. And like, hey, can't be too warm, yes you can. Okay, for the ecology of the organisms, the nutrients, well actually the nutrients don't come up. They stop and it gets too warm. So those two things kind of work against. This is an El Nino condition. It can last for 3 to 7 years. And it actually has consequences other than just being warm here off South America and not having nutrient-rich waters. The other thing it can do is you can kind of see the water here. Okay, what it does is basically storms that would have gone over here. We kind of talk about Indonesia and Australia as kind of being the counterpart to South America. These guys get too much water and these guys don't get enough. Okay, so El Nino events then go ahead and the warm water and the precipitation stay here. They literally over here in Australia and Indonesian islands, they literally see they see more land. They actually see their sea level drop. Okay. So the upwelling shuts down, water off the coast now is nutrient poor, fishermen aren't happy, okay? And yeah, they'll get more rain. In Australia and Indonesia, like I said, I have a word here, will receive less rain. So that's El Nino. So we have neutral or normal, El Nino, okay, and then we have La Nina coming up. And it's a little, it's more complicated than this. So what actually an El Nino event has is consequences globally. You're like, well, it's just the trade winds. So you can kind of see some things that generally can affect worldwide. And actually, if you're a Farmer's Almanac purchaser, okay, Farmer's Almanac, they got a lot of great stuff in there. And one of the things that they base their forecasts on is what is the globe in El Nino, neutral, or La Nina. So if El Nino, we have the trade winds petering or even reversing themselves. A La Nina, again with the trade winds are those associated with the Hadley cells. The trade winds actually will intense. You're like, well, what's wrong with that? Too much of a good thing, okay? So it brings up this nutrient-rich water, but it's cold. And so we actually have cooler than usual temperatures here. Okay, which, you know, that could have problems. If you're over here then, you're going to be drier than usual, less rainfall. And if you're over here, guess what? More rainfall. Again, it's a global situation. This, by the way, the kind of how we have this kind of big cell here. This is sometimes called the Walker cell, W-A-L-K-E-R cell. Just kind of focusing on that region, trade winds between South America, west coast of South America, Indonesia, and Australia. So what happens is actually they end up going back and forth or alternating between El Nino, La Nina. So what I say, 3 to 7 years for this? I think this is even a little shorter. 3 to 7 years, excuse me, for the El Nino. I think it might be 3 to 5 for the La Nina. So the back and forth is called the Southern Oscillation, and that link right there, we'll kind of take a quick look, and I'll show you what they say right now about the conditions. So this is about a week ago, probably ready to come out with a new one, okay? But they evaluated, and it's not just the trade winds they evaluate, it's more than the trade winds. But notice we are in a La Nina period, and they'll kind of talk about sea surface temperatures and winds and precipitation, but that kind of summarizes it right there, La Nina advisory. We're getting ready now. The next part, I'm going to pass it out here in a minute, is actually hurricanes. And I double checked, and hurricanes are affected by what cycle we're in, La Nina or El Nino. As it turns out, La Nina global situation favors our East Coast hurricanes, which most of our hurricanes are from the East Coast. We do have a smattering of West Coast hurricanes, which those are favored by El Nino. So, and I posted it on Twitter, but right now, as of now, our hurricane advisory is probably more than usual. So this is kind of showing you the oscillation between the two. The way this works is the blue is the La Nina, the red is the El Nino. And one way we can track it is sea surface temperatures. So this is color coded. The redder it is, the hotter it is, the bluer it is, the warmer. Oh, sorry. Yeah. The redder it is, the hotter it is, the bluer it is, the colder it is. So you can see here, La Nina, we had an intense trade winds, brought up that cool water. That's why it's cool here. El Nino, we basically petered out our trade winds. We shut down our upwelling, and so it's nice and toasty. All right, so on to hurricanes. It looks like this. All right. You know, with this subject, oh my gosh, the movies out there, the documentaries out there are just amazing. And the last topic we're going to cover is severe weather, not hurricanes for us, but of course with us it's the thunderstorms and the tornadoes and stuff like that. There's great videos out there for that too. So what you're looking at, you can see the map of the United States, North America, South America, Africa, Europe. And those red lines there, red, purple lines, are showing you the paths that the hurricanes take in general. I told you, off the top of my head, it seems like we have, this is the Atlantic Ocean and this is the Pacific Ocean. Of course, it seems like we have more hurricanes affecting us there. Okay, but some places don't get hurricanes. Now, first off, notice that this slide does not call them hurricanes. It calls them tropical cyclones. So that is a hurricane for us. Hurricane is more of a local word, and here in the next slide, I'm going to show you that worldwide, the tropical cyclone is the generic name for a hurricane. We know you have a hurricane if you have winds that are going at least 74 miles per hour. Of course, we categorize hurricanes. That would be category 1. Oh, looks like I need the word is central, excuse me. Very low central pressure. We've used that word before, central, when we kind of talked about these central pressures, right? The warmer the water, actually warm water is an ingredient. And the thing is about global warming then, we are concerned about our ocean temperatures getting warmer. So warm waters are an ingredient, and the way warm waters work is that they actually provide warm, moist air. So you have water in its vapor phase, it rises, and when it condenses, it releases heat. Heat of condensation. So I kind of hit a few things here. The deadliest hurricane ever was actually in Galveston, Texas, in the year 1900. Actually, Galveston got hit twice. Okay, it's number 1 and number 9. So 1900, 1915. And you might, I bet you already kind of know, the death toll was so high there. You figure, for a number of reasons, their structures weren't as sound as they are today. They didn't have the warning system that we have today. I guess those big two, those are the two ones. Hurricane Katrina, I don't know. It's been, goodness, so this is 2018. It's been 13 years, but it seems like it happened just the other day. That made number 3 with regard to the lives lost. So this is actually, I don't know if this is Hurricane Katrina or not. Of course, you know what we're looking at. We're looking down at the clouds of a hurricane, and you kind of see the eye of the hurricane. You can see these are called spiral rain bands coming out. But this is Katrina, I'm pretty sure. Because that looks like the stadium that was famous, infamous for granting shelter to people. There are definitely some awesome documentaries out there about Hurricane Katrina. And New Orleans, the documentary will tell you the city of New Orleans is kind of in a bowl sort of shape. And so they were kind of setting themselves up for potential issues. And the video would also tell you how not just in New Orleans where Hurricane Katrina hit, but people are bad at kind of messing with our wetlands and things like that. So there were many things that went into kind of how Katrina got hit so bad. Okay, so the anatomy of a hurricane. I mentioned spiral rain bands, and actually we're going to see spiral rain bands. There'll be air ascending, okay, and it will be moving counterclockwise into the eye. So counterclockwise, you should be thinking this sort of deal. So at the eye of the hurricane that meets the earth, we have a low pressure down here. The eye is actually calm, and it's like so freaky, right? If you watch the movie The Day After Tomorrow, which is, anyway, they do kind of talk about the anatomy of that large system that had them having a calm eye. The eye wall, so we have the eye nice and calm. Just outside the eye, we have the eye wall, and that's a set of intense thunderstorms. You have your strongest wind, your heaviest precipitation. We're going to talk about tornadoes in part 7, but actually we're going to talk a little bit about tornadoes here with hurricanes. You can have tornadoes embedded in those thunderstorms cells. So what you're looking at here is the orange line is the pressure. So you can see actually as the eye passed over this measuring device, the pressure dropped to 964 millibars. Now, when you guys were doing your lab yesterday, I think the lowest one we had was 996 millibars. That's a very low pressure. The lower actually measuring how low a pressure is one way of categorizing the hurricane. So then you can see that the other line, the red line, is actually then, the red line is wind speed. So I said that the hurricane was calm. So you can see that the wind dropped down to 0 under the eye. The hurricane is calm, excuse me, the eye is calm. So here's where the eye is. All right, so it's a complicated beast. And then we have this other thing called outflow. Now outflow is going clockwise. So outflow occurs at upper elevations, so you can kind of see how conflicted hurricanes are. So we generally have a high pressure up here and we have a low pressure here. So down here we have counterclockwise movement and up here we have clockwise movement. Seems a little twisty to me. So if you want to make a hurricane, what do you need? Well, I mentioned warm water. Specifically, you're looking for something greater than 81 Fahrenheit. Okay, and like I said, that warm water then, above that warm water, think of nice, the warmer it is, the more water vapor you'll have, and the more water vapor you have, then actually it can condense and give you the fuel your storm. So for warm water, you want to be pretty close to the equator, pretty close to the intertropical convergence zone. But if you're too close, then you don't get the spin that you need. When we talked about the Coriolis force, this spin that actually is an apparent deflection provided by this rotation of the Earth, we said that the Coriolis force is most intense at the equators and basically, most intense at the poles and basically 0 at the equator. So you have to be greater than 5 degrees from the equator. So you have those two things kind of need to be in place. And the last one is you need to have what we call relatively unstable atmosphere. I don't think when we talked about the different types of clouds, I emphasized what the word unstable means. But unstable is instability in your atmosphere is basically talking about how the air doesn't want to stay where it is. The air wants to go up. And there's different reasons for that. Okay, so that's an unstable atmosphere. Favors mid-ocean instability. Here in a minute, we're going to talk about kind of how a hurricane kind of is born and matures. But we're going to see it kind of starts out as kind of this little rogue band of little cumulonimbus clouds. Okay, so little band of cumulonimbus clouds. That's what we have right there. I'm going to kind of pick on our Atlantic, the hurricanes that end up in our Atlantic Ocean. But check this out. Where do they start? They start off the west coast of Africa. That's where meteorologists are looking to see if we're going to get hit by a Category 5 hurricane. So these easterly waves, you can kind of see the little wave thing, and those little dots there are actually cumulonimbus or thunderstorm clouds. Well, then actually it can go ahead and mature into a tropical disturbance. Now, the first slide, we started out here, we didn't call it tropical disturbance, we called it a tropical cyclone. So there's actually two things between a tropical disturbance and a tropical cyclone. So you can see the winds aren't going fast enough. Was it 74 miles per hour or greater to make us a tropical cyclone or a hurricane? But these are just then the clusters become more organized, they bump up the wind speed. From a tropical disturbance, a system or a cell maybe at this point can be upgraded to a tropical depression. And you can kind of see the statistics on this. Only about 10% or 1 in 10 disturbances actually get the steam they need to become a tropical depression. Okay. All right. And the thing that's happening is that central low pressure is getting lower and lower. And as your central pressure becomes lower and lower, your winds pick up. So after the tropical depression, then it becomes a tropical storm. So the tropical storm, winds are going faster, and tropical storm is actually, I'm going to add this too because I think this is so cool. Tropical storm is it finally gets named. So it gets a name. Now back in 1914, when Galveston, Texas was slammed into by hurricanes, it took so many lives, we called it the Galveston hurricane, okay? But now, as you know, we have a list of names. We alternate. They start with letter A, then starts letter B, starts letter C. Okay, then hurricanes actually have a systematical name. So they're named there. If they pick up steam, oh, it does say named, finally named. Goodness gracious. If it picks up enough steam, it will become a tropical cyclone, which to us is a hurricane. Tropical cyclone and hurricane mean the same thing. Oops. I think I had 74 miles per hour, now I have 75 miles per hour, but that's okay. Okay. So that's kind of it in a nutshell. So let's talk about some rules of naming your tropical storm, kind of the level before your hurricane. Tropical storm intensifies, goes to tropical cyclone, same thing as a hurricane. So each ocean basin has its own set of names. So this is actually names for the Atlantic Ocean, Gulf of Mexico, Caribbean Sea. They used to be all female names, but now they alternate female and male, and you can kind of see the A. Now, if you look closely, you're going to see that some letters have been skipped, and actually that's a line up here. Because it's hard to come up with some names for a particular, all the words alphabetically. So you got to take a quick look, see if your name's up there. The letters that are skipped are Q, U, X, Y, and Z. Q, U, X, Y, and Z. If we have more than, so that only leaves 21 possibilities. If we run out, if a list runs out, then we draw from the Greek alphabet. The names are recycled every 6 years. So this is how this would work. So this is outdated. My goodness. So that's 2016. So this would be 2017. This would be this year, 18. This would be 2019, etc. And then this is a good one. I like this one too. It's possible that these names can be removed from this list that's being recycled because of the intensity of the storm. Yeah, so there's no, this was after Katrina. There's no Katrina. Okay, a few. Is it okay? There's an Ian. My gosh. Okay. Oh my gosh. Mackenzie? No. Wow. That's amazing though. Ashley? No. So these are the names that have been retired through 2014. So these used to be names. Fifi? Well, I'm not seeing it, but. And already, can you see where we have some years that are just crazy? So 1995, the fact that you had 4 names that were retired, bad year for hurricanes. That didn't, we were beat by 05. Dennis, Katrina, Rita, Stan, and Wilma, all in one year. Equal? Anyway. Let's see. Let's see if I want to put that up. Let's still do this side. So, just looking ahead, the last part we're going to actually talk about tornadoes, and there's some similarities between tornadoes and hurricanes. There are definitely some differences, and one of them is the categorization, how we categorize them. So they are categorized, they're both categorized into 5 categories, but they use different scales. Hurricanes use what's called the Saffir-Simpson scale. And the big thing, or a big thing between hurricanes versus tornadoes is hurricanes last a heck of a lot longer. People are watching for potential hurricanes as they come across the ocean basins. And so actually we measure their intensity as they're there. Versus tornadoes, the only way you know if you have an EF5 was after the fact. You go and you look at what damage it did. So category 1 is the least intense. Category 5 is the most intense. I already talked about, I'll put the word low in front of pressure. You're looking for the lower the pressure, the more intense it is. We'll talk about storm surge when we meet again on Monday. But you can see the central pressure and the storm surge winds. Okay. Wind speeds. So this surprises me, and I need to double check. This is through 05. So is it up to date on that? That's 13 years ago. But as of 05, there had only been 3 Category 5 and 16 Category 4 hurricanes. If you're kind of a weather junkie, kind of following this sort of thing, you know that hurricanes, they can be bumped up in their intensity. Like a Category 2 can be upgraded to Category 3. Category 3 can actually be downgraded to Category 2 or Category 1. So they kind of go up and down depending upon the fuel that they have. Well, that's a good place to stop, I think. We'll pick up here on Monday. So, was there homework due? No homework due. Huh?